So let's talk about the most basic model of regression, which is linear regression. So I have, data examples as before. I have labels as before, y1 through yn. And the only difference between regression and classification, it's of course a big difference, is that these are now continuous valued. Right? And I'm going to allow you to have, potentially nonlinear models by defining feature vectors, right? So I'm going to define, let's think about explicit feature vectors right now. You can always kernelize it. So this is the feature vector for data point x. Right? This is all as before, as we have been doing in the classification setting, and typically, we'll have the same notation as before. These are d-dimensional data points, and the feature vectors are capital D-dimensional, and basically, I'm going to also say that phi I is phi xi is the feature vector for the ith data point. And I know that when we first talked about logistic regression, we were thinking of these x's and phis as column vectors, but it is more conventional in much of the statistical literature to think of these as row vectors. So I'm going to think of this as a row vector, so it's a 1 cross D vectors, and basically I'm going to define the data matrix corresponding to these feature vectors as this phi1 through phi n. The n examples correspond to features that are in rows. So this is an n cross D matrix, where the examples are the different rows of the matrix. And now, what's my linear regression model? I have that I'm going to try to fit yi to a linear model, and I'm going to ask for I'm going to say yi is approximately equal to phi I, remember this is a row vector, times a column vector w, so this is a number. And I'm going to allow a bias also. So this is what I want, that it's approximately, this is the model I have. So then at inference time, I will have a prediction y hat of x is phi of x times w plus b, right? That's, let me change pen color. So this would be at inference, and this is what you'll use for training, that the yi's are approximately equal to phi w plus b. Okay? And the standard formulation here is to say, okay, I'm going to do a quadratic fit. So I want yi minus this estimate phi w plus b, this guy, the squared error of this to be small. I'm going to sum over all the examples, and I will put a constraint to prevent overfitting. So I'm going to put a constraint on the L2 norm of w. So that constraint is reflected through this Lagrangian with this lambda as a Lagrange multiplier. So I'm going to call this L, which is based on w and b. Now clearly the bias term can be modeled implicitly by just putting a constant term into each feature vector, right? It can be absorbed into w by putting constant term, but I am keeping it here to sort of reveal the role it plays. So bear with me and we'll soon get rid of it. Now this Lagrangian, it's a very nice quadratic function of both w and b. And so I can just get to the global optimum by just taking derivatives and setting the derivative to 0. So let me knock off the bias term first. So let's take the derivative of this with respect to the bias term. What's it going to be? It's going to be summation over all those terms, and then 2 times yi minus phi w plus b. That's basically, I took the derivative with respect to this term, and now I'm going to with respect to the minus of this term, and then I'm going to take the derivative with respect to b of that term, and that's going to be minus 1. Doesn't really matter in this case, it just goes away, and then I'm going to set that equal to 0, right? Okay, so getting rid of the factor 2 and minus 1, just, right hand side is 0, so I can divide out by those factors. What do I get? I get summation I equals 1 to n yi minus phi w, that's this term and this term, and then I have I have also minus b, but that's happening n times. Minus n times b is equal to 0, and so when I take it over to the other side, I get b is equal to 1 over n summation I equals 1 to n yi minus 1 over n summation I equals 1 to n phi times w. And so what's appearing here is really these average or mean of the targets and the mean of the feature vectors. So we'll see that when you plug this back into the cost function, you basically, what it tells you to do is get rid of the means. Okay, so this is the optimal value of b for a given w. I'm going to plug that back in here and get L of w alone, which is L of w times and b opt, is going to be summation I equals 1 to n yi minus phi w minus b opt, right? Minus b opt is y bar minus phi bar w. That's what this b opt is, right? Y bar minus phi bar w. That's what we have defined it to be. I'm sorry, y bar is this entire thing, this average, right? And I'm squaring that, and I still have the regularization term as before. So look what it's telling me to do. It's basically telling me by yi minus y bar, I gotta get rid of the mean there, minus, I can also do phi I minus phi bar there times w whole squared, and then plus lambda w squared. So the role of the bias term is just to say that please get rid of the means before you do anything. So these are basically demeaning operations. Okay, so to simplify our lives, I'm going to assume demeaning has been done. So that simplifies the notation, and say I'm going to optimize over w the following cost function I equals 1 to n target minus linear model plus constraint term, right? That's our optimization. It's a quadratic in w, and it's easy enough to compute the gradient and set it to 0. So we are gonna do this, take the gradient of this loss function and set it to 0 to get the optimum value of w. Let me just do some calculations on the side. We've already done gradient computations before, but there's no harm reviewing them. So when I look at a term like phi w, what is it doing? It's basically taking this phi is a row vector. It's taking phi 1, multiplying it by w1, the first element of w, phi 2, multiplying it by the second element of w, etc. So note that del by del wj of this of phi w, this number is just going to be the jth entry of phi, right? So basically the gradient of phi times W is just the elements of phi, but of course phi was a row vector and this is a column vector, so this is just phi transpose. Okay, that's one thing to note. And the other thing to note, of course, is this guy, the norm squared term. Well, this is just W transpose W. So basically, it's Wi, the element squared. So this is just going to be 2 times W. It's pretty easy to check. Or you can think of it as two W terms, and you differentiate with respect to each, and each time you get W, and that's how you get the 2W. One way or the other, that's easy enough. So we do that. Now we go back to the cost function and compute the gradient. So basically, I'm going to compute the gradient of each of these n terms. Again, chain rule. I have -2 is the times yi minus phi I w is the derivative with respect to phi I w, and the gradient with respect to phi I w is, of course, phi I transpose. We have shown it, plus 2 lambda w is the gradient of the other term, and I'm going to set that equal to 0. And now you note we just want to put this in a convenient form. Remember that this is just a real number, and this is now a column vector. It's convenient for me to bring it over here. Perfectly legitimate for me to put the column vector in front of the real number. And let me just collect all the terms, get rid of the 2, and what do I get? I get summation I equals 1 to n. The terms multiplying W are phi transpose phi times W plus lambda W. I've gotten rid of the 2 everywhere, okay? Minus summation I equals 1 to n phi transpose yi is equal to 0. And now we are ready to express it in matrix form. Remember that your matrix phi was all these phis, phi1 through phi n as rows. So this, let me change pen color quickly. This guy can be written as phi transpose phi. What can this guy be written as? Phi transpose y, where y is just the labels expressed with the labels for various examples as rows. So basically y is just a column vector of length n. And so the whole thing boils down to phi transpose phi plus lambda times the identity is multiplying W. And let me call it W opt now. This is the optimum value. Is equal to, I'm taking this term over to the other side, is phi transpose y. Right? And that's my least square solution. You may or may not want to invert it. You may think of you may or may not want to invert this matrix. You might just want to solve this set of equations. But basically, you have, in some sense, you're correlating this term is correlating the labels against the feature vectors, and essentially multiplying the ith feature vector with the ith label. So it's sort of a how do the labels correlate against the feature vector? That's what this is telling you, and this is basically looking at the second order properties of the feature vectors, and then there's a regularization term which is the lambda I term, right? So this is the second order properties, this is a regularization term, and this is a correlation between the feature vectors and the label. Just a quick dimension check. Remember, phi is n cross d, y is n cross 1, phi transpose is d cross n multiplied by n cross 1 gives me D cross 1 vector, which is good. Phi transpose phi is basically D cross n times n cross D, so that's D cross D. So this is a D cross D matrix multiplying a D cross 1 vector, giving me a D cross 1, and it's being set equal to D cross 1 vector. So it's all working out. And let me just write out what W opt is. Remember, this is all assuming d-meaned features and labels, right? W opt is, of course, phi transpose phi plus lambda I inverse phi transpose y, and that is again worth boxing. It's a solution that you see come up often in the context of least squares problems. And of course, for a new point, x star. For inference, I have phi of x star, I'm calling it phi star, my y star, the target for that, y hat star, is going to be phi star times W opt, right? So that's what your estimate would be. Again, assume D meaning, right? So that's what you don't have the bias. You don't need the bias term when you do that. One quick implementation note, in addition to the D meaning, we often also normalize the individual components of the feature vectors to have the same variance across the training set. Otherwise, you might weight one too much compared to another, right? So that's again discussed in the handout. So one last thing, I've been carrying around all these summations over all these examples, but before finishing up, I would just like to put the whole thing in vector form and vector matrix form, so we get a simple, elegant solution. Let's just do that. So remember that your loss function after d-meaning and all that, after you've taken care of the bias term, that was phi I times W minus yi squared, sum I equals 1 to n, plus lambda L2 norm of W squared, right? That's what it was. I have flipped the sign around for this term, but it doesn't matter because I'm squaring it. Now, remember that your phi matrix contains all these phi i's as rows. So you can see that phi times W is just phi 1 W down to phi n W. So it's a column vector, right? Like that, with these are the estimates corresponding to each of the examples. Similarly, let me define we know that the target vector is y1 through yn, and we are just taking the term by term error, let me change pen color, between these two guys, so that this sum is simply phi W minus y L2 norm squared, and then you have the lambda W squared as a regularization term as before. So this is how you would write the loss function in matrix vector form. And now taking gradient is rather simple. You have to write the norm squared terms as A transpose A. Norm squared of A is that. So I can write this as phi W minus y transpose phi W minus y plus lambda W transpose W, and then let me just write it out a little bit more. So this is W transpose phi transpose minus y, that first term, times phi W minus y plus lambda W transpose W, right? And so now I'm going to leave it to you to check that the gradient of this with respect to W is just, when I take the gradient with respect to W transpose of changing pen colors again, of this term, I'll get phi phi transpose, and then I have phi w minus y. And really, this is happening twice. I can take the gradient with respect to this w also, and I'll get the same term. Remember, those terms are essentially completely symmetric. Anyway, I'll let you check all that. So I get 2 there, and then I get 2 lambda w from the second term, and that has to be equal to 0. The 2's cancel out, and I get phi transpose phi w plus lambda w, and taking the y term over to the other side is equal to phi transpose y, which is exactly the same thing we had. Phi transpose phi plus lambda I times w opt equals phi transpose y. So really, this is the way to really formulate it for coding things up. You're not going to do the sum over all the examples explicitly like I had done before, but I just wanted to do it in that way, in the sum form, just to make everything very transparent. But really, we want to be formulating everything in matrix vector terms, like we have done before. So basically, like what we have done here. So this form for the loss function, and that immediately and very quickly gives you this optimal solution. One last note: I'm not really into these technical names too much, but I should just note that what we have just talked about, this linear regression subject to this L2 norm constraint, is often called ridge regression. So it's just a term worth knowing because it's used quite a bit.